In today's recording, we're gonna tackle the new section in the embedded system course on the embedded buses or the communication port. Alright, so first things first, what are the basics of communication? What do we need the communication for? As for humans, we need to make sure that whatever someone is saying to the other person is getting it correctly. So we don't want to be this guy here. Alright, so when it comes to digital systems, we've mentioned it in the DSD course that you've taken with me 2 years ago. And we know that there are two different ways when it comes to communication between two different entities, digital entities. The first one might be might be thought of as the faster one, which is the parallel communication. In this case, what we have here is a transmitter sending at once in one clock cycle all of the bits of the word, and then the receiver will get those at once as well, from theoretical point of view, of course. Right? So here we can assume that the word size is 8 bits, and each clock cycle I'm able to send my 1 byte data directly to the receiver. Fair enough? So I'm not cutting my data into chunks to send them in a different way. So if we have a parallel communication here, and you can notice that we need to specify, of course, we have the clock, right? Because it's a digital system, and in this case we need to, send the stuff during the clock cycle. But this is not necessarily the case all the time. And then we need to specify the order of the bits, also known as the endianness, right? So which bit corresponds to the least significant bit, and which one corresponds to the most significant one. What would be the second type of communication? That would be the serial one. Here we've broken down our bytes of data into a bunch of bits sent one after the other using only one wire, in addition in this case to the clock. So on each clock cycle I'm sending only one bit at a time. So you can notice from theoretical point of view there are some differences between the two. Again, from theoretical point of view, this feels like the parallel communication is X time faster than the serial one, and in this case, because of the number of the bits here, X is 8, so this one is 8 times faster than that one. It feels like it. So it takes one clock cycle to send 8 bits here, whether it's taking 8 clock cycle, so it takes 8 clock cycles to send the whole byte, right? And again, I need some kind of indicator which bit corresponds to the least significant one and most significant one. And we can feel here from the schematic that the first byte to be sent is the least significant one. The first bit to be sent is the least significant one. Alright? We could have chosen a different way to start with the most significant one. It's an engineering choice. Right? Fair enough? Alright, so let's see. I'm gonna check the first 2 points here and trying to guess whether this describes the serial or the parallel communication paradigm. So data transfer is very quick and setup is more bulky. So let's see, very quick. Apparently from a theoretical point of view, we've seen that parallel is faster than serial, and setup is more bulky. So in the parallel we used much more wires than in the serial one, where we needed only one for the clock and one to send the bits. So yeah, so this is definitely related to the parallel communication. And two new things we're looking at here, and in the face-to-face lecture we spent some time trying to understand those and trying to guess them and then understand them. So there's the clock skew here, so it's a risk, so it's a disadvantage here, and something called crosstalk. Alright, so I'm gonna start with the letter. So here, crosstalk, we can guess from the name it's something that is crossing, some kind of interference between the different wires, because we're using more wires, so the chances of the different wires generating electromagnetic fields and interfering with each other is higher. The risk here is higher than in the serial one, when you have only two wires, so the risk is minimum compared to the parallel one. So this is crosstalk, so interference between the wires. What will clock skew be? So to give an example in class, after someone guessed it correctly, so clock skew happens because of the fact that we have different wires, and each wire, and we've learned it from the DST, has some kind of propagation delay. So if I'm sending a bit here and a bit here, bit here, bit here, all at the same time here, however, because of the different propagation delays, so the bits will arrive different times that do not necessarily correspond to the exact clock cycle. Alright, so this is what we call the clock skew. And to have some kind of analogy for that, imagine that you and your colleagues, you're gonna have some kind of marathon, or just like to run, right? So we have a couple of people here, and they are all at the start line here, and then they start running. Even though you must probably have the same age, you all study at the same university, etc., etc., but because of the nature, right? So some of you will get to the finish line before the others. Fair enough. So this is the clock skew. Another thing regarding especially the propagation delay and the clock skew here, we can notice that if the distance of the finish line is extremely small, the effect of the propagation delay can be non-perceivable. We cannot necessarily perceive it, in the sense of, if it's too short here, we won't notice a lot of difference between the different bits getting to the finish line, if we dare to say it like that. However, the longer the distance is, the more we can perceive the effect of the propagation on the different things. Fair enough? And the fact that we're using different wires makes this risk extremely important in the parallel communication. Do we have a big risk in the serial one? Well, because we're using only one line for the data, right? So only few wires, 1 to 2 wires, one for data at least, and an optional one for clock. We'll see why an optional one, right? So we don't have those problems. The crosstalk is not a big risk anymore, because we don't have a bunch of wires anymore, and the propagation delays between the different things is not a big deal anymore in the serial communication. Alright, hence we can use them for longer distances, right? And this is true. So basically, if you're gonna check some standards, and I really hope that everyone knows what a standard is. So you have a couple of standards out there, international ones. So this is the IEEE one, for instance, and you have different standards from the ISO, the international standard, or standard organization that is Switzerland, for instance. So you can see that it's a maximum 20 meter, right, total for any parallel communication and between two devices. Between for the whole thing, and with a maximum of 2 meters between any two devices, because you might have more devices, like in a daisy chain or something like that. However, for serial, we can go to even a little bit more than 1 kilometer. So yeah, we have a feeling that serial is a little bit more interesting than parallel, and it's a question, it's a very recurrent question that I keep on asking each and every time in the face-to-face, and we try to argue about that, is what do you think, which one is better, from an absolute point of view, serial or parallel? Well, as good engineers, we should always answer, there's no one truth out there. It's it depends on the situation. So it depends on the application, the context, the engineer system that you're trying to develop, etc. However, here we can feel that if we're gonna communicate in somehow long distances, relatively, right, it's better to go serial. If we don't have much space for a bunch of wires, it's better to go serial. If we want to minimize the effects of interference, it's better to go serial. That's why in this course we're going serial. Alright? By the way, there are still some, and most of the applications or communication protocols in the real world now are tending towards serial. And a proof that something that is omnipresent now, it's everywhere, it's very ubiquitous, is the USB, which is the universal serial bus, right? So it's serial. Right. Where was I? So yeah, does this mean that parallel is no good, we should never use it and never ever ever? No, it doesn't mean that. It really depends on the application and the context. Right. Question number 2. So we've seen in the very second slide parallel and serial communication, and we've seen the presence of a clock. Systematically, by now, everyone should know that if there's a clock, this means that the system is synchronous. Fair enough. However, it doesn't, and I said it, it's something optional. So we don't have to have a systematic clock each and every time. So this is when we can have asynchronous protocols as well. Alright, so asynchronous communication. And of course there are cons and pros. Synchronous means that everything is in order in a way or another, at least from a theoretical point of view. Asynchronous means that I need to manage the order manually because I'm not synchronized with the clock. However, asynchronous means that I can send whenever I want and not necessarily map my sending on a clock. Map it to a clock. So this means a higher flexibility in a way or another. Alright, whatever the protocol is, say asynchronous or synchronous, we should always have some kind of coordination happening between the sender and receiver. For what reason? Take a second or two to think about it. Right? So imagine that someone got you, introduced you to someone new. So there's some kind of protocol to follow, right? It's a human protocol to say hi, to introduce yourself, to see if the person is a local or a foreigner, maybe to choose a language that you both understand, stuff like that, right? Same things should happen in the engineering world, right? So when to start talking, when to stop, so when to start transmission and when to stop, how big the words should be. So remember, at Mega, for instance, we've seen that the word size is 1 byte, 8 bits. In other architectures, they could be 16, 32, I don't know. something like that, right? So when a particular word starts, when does a byte start, and when does it end? And then to see if the receiver is able to follow up, right? So to make sure that you're on the same frequency, so you're not talking too fast for them to understand, or too slow for them to get bored and zone out, right? So let's see. So a protocol is some kind of convention or a bunch of specific methods to coordinate the data transmission between a sender and a receiver, right? So we can have asynchronous sent, sending and transmission. So sending and reception or receiving, right? So asynchronous, we don't need a clock. And if we're talking serial, and from now on we're talking serial, so we only need one signal to represent the data. I mean, to send, or one medium, one wire to send the data, to vehicle the data. Or synchronous in that case, we need two different things. One, to have the pulse, also known as the clock, right? And the other one is the wire that vehicles the data itself. So which is better? By now everyone should be there. A little voice in your head telling you that there's no absolute better. It's a it's based on the context or the situation. Alright, so I've showed this picture in class and no one was able to identify it. So basically this is some USB looking something. It looks like a USB, but it's not a USB cable. Back in the days when you were really, really unborn yet. So 80s, alright, late 70s, early 80s. Apple's, Sony, and a bunch of Panasonic, I believe, they created something that we call a firewire, and this is a protocol and a cable. So a protocol to be able to connect external peripherals to a computer, such as external hard disk and stuff like that. So yeah, and every company or a bunch of companies, they had their own protocol or standard. So before the whole USB omnipresence. Right, so I'm gonna show you some serial communication protocols that exist out there, and we're gonna tackle a couple of them in this course. So RS something, RS. All right, so the firewire, and this is the one that I showed you here. Ethernet. So most of you apparently you've taken a network class, so you know what that is, hopefully. Yeah, so Ethernet is a serial communication protocol. So someone might be shocked because we just said that a serial communication protocol has extremely few wires, and if someone is curious enough and have seen, cut open an Ethernet cable, you will see a bunch of twisted twisted wires inside it. So how come it's considered to be a serial communication protocol? Well, the trick is you have a bunch of wires inside an Ethernet cable, that's for sure. However, you should ask yourself, what is the length of the data word? So am I just sending one byte at a time through the cable, or is it more than one byte? Is there a sufficient number of wires to send the whole word at a time, or we need to cut it down to smaller chunks to send them? Well, in Ethernet, yes, we do that. We actually cut a whole packet. I think you know what a packet is. the data into different packets, I mean, and then you send it through the cable using the protocol. So yeah, it is a serial communication protocol. And by the way, why are the RJ cable twisted for the Ethernet? Um, so the whole point was to try to cancel out the electromagnetic field that might stem from the different wires inside it. So it's a kind of safety mechanism in order to make sure that there's no interference happening or minimize the interference that might happen. All right. So MIDI. So some of you who are interested in music, they heard of or they manipulated MIDI files. So this is a communication protocol that is meant to be used with a synthesizer. It's a hard word to say, synthesizer, right? And to be able to communicate with the different modules that produce different types of that represent different types of instruments. PCI Express, so it's something that you might see inside of your computer, desktop computer sometimes, right? So P stands for peripheral, and CI, I have no idea. Well, I do. Go ahead and figure it out. SPI, we've seen that one somewhere, I think. All right, so S stands for serial again. I2C, also known as the wire, we've seen that somewhere, and the CAN bus as well, right? So those three here, they're UART based, and we've seen UART in a way or another before in this course. We also seen SPI and I2C or two wire. When did we see that? I mean, it was when we talked about the Atmega features, and some of them were there. We're gonna get back to that later on, so don't worry if you do not remember. Alright, so yeah, predominantly serial. So how does serial work? So we need to agree on a couple of things, right? We need to coordinate before the transmission happens. Yeah, take a second to think about the different things that we should take care of. So remember, there's some kind of communication happening between two different entities. So one question might be, is it a one-way communication or a two-way communication, right? And I think that you've seen something like that in your network course. It's not a course. Whether it's a full or half duplex operation, or even sometimes a simplex operation. Right. One other thing that you might think of is the frequency of how fast the communication is. Now from now on, I'm gonna circle it like a zillion times, or highlight it even better. From now on, whenever you speak communication, you speak in terms of communication speed. You speak of in terms of baud rate, right? So now it's baud rate. So baud rate, it is the unit that was named after Jean-Maurice Émile Baudot, and he's a French telegraph engineer, and he's the inventor of the digital communication Baudot code, right? And he also invented a multi-text printing telegraph that allowed multiple transmissions over a single line, right? So that's two. A third thing definitely is something that we've seen in the very second slide today, is the order of the bits. So whether it's big endian or little endian, right? So which one, what represents the MSB or the LSB? Right, so what is the size of the word in a way or another? So how many bits to encode a character, a word or something like that? A laser pointer, alright? And lastly is we're gonna imagine that we said high, right, when we agreed on the different parameters, and then we need to know when to, to verify if there's something wrong happened in the transmission or not, right? So a parity bit is some kind of checksum, to verify if everything went well. Alright, so let's see the different things. Full or half duplex. So this is a simplex, one way, unidirectional, one sender, one receiver. There's only one medium here, right? One communication medium. Let's go for the full now. So the full, if this is a one way, a full would be two ways. Fair enough? So this entity could send and receive, maybe in parallel, most definitely in parallel. Depends if you want. But I mean, it's enabled to do that, right? Depends really on what you're trying to do here. Alright, so this is two different media. So medium number one, medium number two, right? Bidirectional. And what would the half duplex look like? Could be a combination of the two, right? So yeah, we still have two things here and two things here. However, in the middle, we only have one medium here. So it's either sending at a time or receiving, right? One at a time. We can do those in parallel. Fair enough? Alright, so the baud rate, it's an important aspect. So this is the speed of the transmission, right? We've already seen what TX and RX, we've seen it somewhere in this course when we talked about the Arduino board, and we've seen the LEDs named TX and RX to show if something's coming to the board or going from the board, right? Coming to the microcontroller that is on the board, right? The whole idea here that I need you to understand is the baud rate corresponds to the transitions that happen per second. So how many transitions could happen in a second? Alright? When you check your network speed or something like that, your internet speed, whatever, you've all heard the unit BPS, right? So it's bits per second. So this means that the changes and the symbols that I'm tracking are bits, right? So how many symbols can transit per second? And if and only if a symbol is equal to 1 bit, alright, this means that the baud rate is equal to the bit rate. If and only if a symbol is equal to 1 bit. This is important. This is why I'm having a second slide for it. Alright, so if the symbol transiting is not equal to a bit, this means that the baud rate is different from the bit rate. Fair enough? Most of the time, in real life, most of the time, not all the time, most of the time, the baud is equal to 1 bit. Most of the time. So the baud rate is equal to the bit rate. Most, not all. Alright, so let's see here. This should be NR. Right, so RX here, not TX. Right, so let's see here. Try draw conclusions. If we see something like that in an exam or later on in your job, someone gave you a schematic, a weird looking schematic here. We can deduce some stuff. We can try and draw some conclusions. First off, TX and RX. This means that there's some kind of transmission happening. So TX transmit and here receive, right? Apparently the data, most probably, this is a but my guts is telling me that the word size here is one. So 8, so 1 byte, right? And this looks like a serial communication because I only have one wire. This looks like an asynchronous communication because I don't see any information regarding the clock. So there's only one wire to transmit the data apparently, in this way or that way. Alright, so this way, that way. This means that most probably it's a full duplex. Alright, bidirectional, at least bidirectional enabled. Alright, and that's it. And these are two different entities. We good. So this brings us to UART. We're talking about the UART, and this is the one of the serial communication protocols that I told you that we're going to tackle in this course. Alright, and of course it is the communication protocol on the Arduino board that you use to connect your Arduino board to your computer, by the way. Alright, so let's see what does it stand for. So we can try and guess the letter here, the letters. So I'm interested in the A here. RT, they look like the RT here, so we good. The A and the U. So U is for universal, A is for asynchronous, receiver, transmitter. So we good. Alright, and alright, hold on a second. So I just said that this is a communication protocol. Why am I calling it an IC here? So an IC is an integrated circuit, right? So yeah, the IC is the implementation of the protocol in the sense of is the hardware module that I need to be present in my microcontroller that enables the UART to happen. Right? So if you look in your data sheet, whatever the microcontroller or the system that you're using, and you see that there's a module that is called the UART, this means that the whole microcontroller is able to communicate with other entities that they have UART as well. We good? Serial, asynchronous, serial. Alright, so yeah, it sends packets naturally. Alright, because again it's a bus, it's a network, so it's easier to reason in packets. And as we've seen that it's full duplex. What if I don't need to use the full duplex? What if I only need this entity to send data and never need to receive anything at all? So I might only be using it as a simplex. So see, think about it. So it can go all the way up to full duplex physically, but we can use it for different things as well. And this is how your packet, the packet is made of different fields here. So we can remember we need to have some kind of way to say that this is the beginning of the convo and this is the end of it. So beginning of the packet, end of the packet. I have a field that represents the actual data that I'm sending. As I told you, I have some kind of lightweight safety mechanism here, the parity bit, which is apparently optional. I can either use it or not use it. And then, yeah, there are some weird stuff that you should be noticing here and starting asking questions. Maybe ask yourself questions because I cannot hear it. Right, so yeah, so first off, what? This is 5 to 9. This means that this changes. Yep. Remember when we said that we need to coordinate between the sender and the receiver? So we need to make, to agree on or to fix the size of the data that we're sending. So whenever we're setting up the communication here, we need to say that, well, the data length will be, let's say, 5 or 6 or 7. I mean, naturally, you can think that as engineers and especially as embedded systems and BSD engineers, you would think that it makes sense to have the length of the data here as 1 byte, so 8 bits, right? But however, these are options, possibilities. This is flexibility. For some reason, if you need to have your data bit field here only 5, you can do it. All right, this is good. And here we have 1 to 2 bits. It's optional as well. This means that you can either choose only one stop bit or 2 bits to make sure that you're stopping in a way or another. It's another safety-like mechanism, means saying that, all right, so goodbye to make sure that the person heard you or the other entity heard you. You can see it like that. All right, so start bit. Whenever the communication line is empty, it's maintained as on a high voltage, right? Because remember, everything is represented in different voltages. So what happens here is I need to make sure that whenever the line is empty, so this is the transmission line, I'm always keeping it at high. How would I mark the beginning of the packet? So I need to break this high stream that I have here, this high state. So all I have to do is to bring it down for for some time, to say that this is the beginning of my packet. Alright, so to initiate, I need to pull it down from high to low. 1 clock cycle from the sender point of view. Alright, because remember, the sender is still synchronized internally using the oscillators, etc. Alright, so this is my start bit, and hence when the receiver will see that, they will be expecting next the data field. They agreed upon bits, number of bits to represent the data. Good. And most importantly, the receiver, they're gonna start trying to read whatever is sent at the agreed upon frequency, but from now on we're gonna use the baud rate. Alright? By the way, what happens if the receiver has a different baud rate from the sender? What would happen? There will definitely be some kind of misinterpretation, in the sense of, maybe some of you tried it, to make the Arduino board print out something on the computer monitor, connect to computer monitor. So you might see different weird symbols appearing if you don't have the same baud rate on the the serial monitor on your computer and the baud rate of your program, of the system that you created on the board. Alright, so the data frame, it's 5 to 8. What? You just told me it's 5 to 9, now you're telling me it's 5 to 8. So yeah, 5 to 8 normally if I'm using a parity bit. However, if not using the parity bit, this gives me one extra additional bit that I might use for my data field here. Alright? General case 3 significant bit transmitted first. Check your data sheet. This is useful data. Of course, this is what we need to send, so to use over there at the receiving entity. Alright? We good? And the parity, well, as I said, it's a kind of safety mechanism. So if there's some alternation, something changed during the transmission, one way to detect it, it's not a guarantee, but it gives you some kind of safety in a way or another, is to check the number of ones. Alright, so the sender will check the number of ones and will check the data, the parity field. So if whatever mathematical formula I apply to the data field here gives a result that corresponds to what has been sent, to what I'm reading here, this means that they match, nothing's wrong. Apparently nothing is wrong. It's not a guarantee, but apparently nothing is wrong. If, however, the red parity bit does not correspond to the thing that I'm expecting, right, this means that they do not match, this is a guarantee that something went wrong. Right? So the parity bit, it's calculated using a way you can always get the data sheet to see the XOR that is made over there to get it. Just to give you a hint, if there's an even number of ones in my packet, well, I'm gonna set the parity bit to 0, so I'm keeping the number of ones even in the packet, the whole packet. and if there's a odd number of ones, right, I'm gonna put my parity bit to 1, so I will have an even number of ones in my packet. However, the number of ones in the data field will be odd. Alright, and this is made using XOR's thingy. You can check the datasheet if you're interested in that. Alright, we've seen in the case of the start bit that the data line is maintained at high, and then we need to bring it to low to mark the start bit. Well, you can figure it out yourself. For the stop bit, it's the other way around, so we need to bring it from low to high. Fair enough? Do it repeatedly. I mean, on two things. Alright, so hold on. In the Atmega datasheet that I'm having here, and this is the Atmega of the 328P. So this is the one that's been used on the Arduino Uno board, right? It's called a USART, right? So what would be the S here? So we already know UART. What is the S? So the S stands for synchronous. So it's a way to say that your protocol here might be used either in a synchronous or asynchronous way. I personally seldom seen people using the USART in a synchronous way. Most of the people who use the USART, they use it as a UART, right? So an asynchronous one. There are other protocols that are made to be synchronous, and they are better used in a better way, right? So the beauty of UART is that you can use it asynchronously, and you use it asynchronously. So yeah. And if we going to check how many UART modules or USART modules are there in the on the Atmega microcontroller that we have here. So according to the datasheet, watchdog timer, awesome, I know what that is. Oscillator, yes, of course, I know what that is. A flash, I know what that is. EEPROM, I know what that is. Oh, USART, hey, here it goes. So I have my USART, and I have only one USART module here, and it's connected to the port D. So basically, if I ever gonna use it, it will be through the port D, and these are one of the alternative functions, remember, that a port can have. Now the question is how many other communication modules do you see according to the ones that we talked about in this lecture? So here you can see the SPI, for instance, connected to port B, and the TWI. This is the I2C, right? It's connected to the port C. Right, so that's it for today. Next time we'll see how to program the different things when it comes to the UART and using the Arduino language. And of course, if you want to do it in embedded C, all you have to do is go and check which registers are concerned with the UART feature, or USART in this case, and then put the right combination of ones and zeros in order to have the feature that you want to use. Alright, have a nice one. See you soon.